Welcome to the NPTEL MOOC on Discrete Mathematics. This is the 7th lecture on number theory. First, we will consider a theorem regarding Euler's phi function. If m and n are relatively prime, then phi of mn is equal to phi of m into phi of n. For any two positive integers m and n that are relatively prime to each other, phi of mn is phi of m into phi of n. So let us prove this. Let us say A, B, C are three sets. They are three reduced residue systems modulo m, n and mn respectively. Then the size of A is phi of m, size of B is phi of n, and size of C is phi of m into n. Let us say X is some member of C, the reduced residue system modulo mn. Then GCD of X and mn is 1 by definition. So X does not divide m and n. There is no common factor between X and mn. Therefore, GCD of X and m should be 1 and the GCD of X and n should be 1, 2, which means X is R mod m and X is S mod n for unique R and S, where R belongs to A and S belongs to B. If X is relatively prime to m and X is relatively prime to n, then X belongs to the reduced residue system modulo m and X also belongs to the reduced residue system modulo n, which means in these residue systems A and B that we consider, there are some elements, unique elements R and S, so that X is congruent to R mod m and X is congruent to S mod n, which means the size of C is less than or equal to the size of A cross B. Because we take an arbitrary element X belonging to C and correspondingly we find an ordered pair RS belonging to A cross B. Therefore, the size of C must be less than or equal to the size of A cross B. But what is the size of C? That is phi of mn. This is less than or equal to phi of m into phi of n. So that is what we have established. That is one way. Now let us take an ordered pair RS belonging to A cross B. Then by Chinese remainder theorem, X is R mod m and X is S mod n. These two congruences have a unique solution in 0 to mn minus 1. So if X naught is that solution, then GCD of X naught mn is 1, because GCD of R m equal to 1, R belongs to A and GCD of S belongs to n. GCD of Sn is 1 because S belongs to B, which is a reduced residue system modulo n. Therefore, X naught is relatively prime to mn, which means there exists an X naught prime belonging to C such that x naught is congruent to x naught prime modulo Mn. C is a reduced residue system modulo Mn. Therefore, there should be an x naught prime which is congruent to x naught in that. This establishes that the size of C is greater than or equal to the size of A cross B. That is, for each ordered pair Rs belonging to A cross B, we have been able to find an element x naught prime. In other words, phi of Mn is greater than or equal to phi of M into phi of N. So, combining both, we have the theorem: when M and N are relatively prime, then phi of Mn is equal to phi of M into phi of N. Another interesting theorem which allows us to calculate phi easily: for n greater than 1, phi of n is equal to n times the product over all p which divides n of 1 minus 1 by p. So, this makes it easy to calculate the phi function for even fairly large numbers. From the definition, we know that phi m is the number of positive integers greater than or equal to 1, less than or equal to m, that are relatively prime to m. We know phi of 1 equal to 1. Say the given number n is prime factorized in this fashion: p1 power e1 etc. up to pr power er, where pi is the ith prime number. So, this is the prime factorization. Therefore, pi and pj are not the same when I not equal to j, which means the GCD of pi power ei and pj power ej is 1 when I not equal to j. So, by the previous theorem, we can express phi of n as the product over I varying from 1 to r of phi of pi power ei. But what is this quantity? Let us compute this first: phi of p power e. So, here we consider all integers less than or equal to p power e, all positive integers less than or equal to p power e, and from this we remove all numbers that are divisors of p power e. The size of the resultant set is phi of p power e, that is, we consider the reduced residue system. Then the reduced residue system will have these many elements: p power e minus the size of all divisors of p power e. But what are the divisors of p power e? They are p, p squared, etc. up to p power e. But what is this quantity? That is p power e divided by p. So, this can be written as p power e into 1 minus 1 by p. So, that is the phi value of p power e. Therefore, coming back to this equation, we can write phi of n as product of I varying from 1 to r of pi power ei into 1 minus 1 by using this formula. But this is pi varying from I varying from 1 to r of pi power ei, and again pi varying from 1 to r, I varying from 1 to r of 1 minus 1 by pi. But the quantity within the first brackets is nothing but n. So, this is n multiplied by the product over I varying from 1 to r of 1 minus 1 by pi, which means we are considering all prime numbers that divide n. So, this product is actually over all prime numbers that divide n. For each such prime number, 1 minus 1 by p has to be multiplied together. So, this product is what phi of n is. For example, let us calculate phi of 10, which is taking the prime factorization of 10, this is phi of 2 into 5. Then that would be 10 multiplied by 1 minus 1 by 2. 2 is a prime which divides 10 and 5 is a prime which divides 10. Therefore, this is 10 into half into 4 by 5. So, phi of 10 is 4. Let us now compute phi of 400. Phi of 400 is phi of 2 power 4 into 5 power 2. So, there are 2 primes here, 2 and 5 again. So, this will be n into 1 minus 1 by 2 into 1 minus 1 by 5, which is 400 into half into 4 by 5, 200 into 0.8, which is 160. So, phi of 400 is 160, which we had used in an example earlier in one of the earlier lectures. Phi of 2 power 4 multiplied by 7 power 6 multiplied by 13 power 3 is this number, 2 power 4 into 7 power 6 into 13 power 3 multiplied by 1 minus 1 by 2, which is 1 by 2, 1 minus 1 by 7, which is 6 by 7, and 1 minus 1 by 13, which is 12 by 13. That would be 2 power 3, 7 power 5, 13 power 2 multiplied by 6 and 12. So, this is the phi value of this number. Now, from this we can prove another interesting result. If n is a positive integer, sum of phi of d over all divisors d of n is n. The proof goes this way. First, consider numbers of the form p power e. So, n is p power e, let us say. Then we are summing over all divisors of n of phi of d. So, this would be phi of 1 plus phi of p plus phi of p squared, etc., all the way up to phi of p power e. These are the divisors of n when n is of the form p power e. 1 p, p squared, etc., are the divisors of n. But phi of 1 is 1, phi of p is p minus 1. As we have seen before, phi of p power e is p power e into 1 minus 1 by p. So, phi of p squared would be p squared into 1 minus 1 by p, which is p squared minus p. Then we have p cube minus p squared, culminating with p power e minus p power e minus 1. So, we find that the some telescopes 1 and 1 cancel, p and p minus p cancel, p squared and minus p squared cancel, p cube cancels, p power e minus 1 cancels. What remains is p power e, which is nothing but n. So, the theorem holds when n is of the form p power e. Now, suppose n is of the form k times p power e for integer k such that p does not divide k. So, k and p power e are relatively prime to each other. Then our required sum over all divisors of n of phi of d can be written like this. First, consider all divisors of k. So, this is a part of the sum, but then That is not the whole of it. We also consider all divisors of PD that have not been considered before. That is, for every divisor D of k, we consider PD. Continuing like this, if you sum in this fashion, we would exhaust all divisors of n. So, all these sums are over divisors of k. But then since D and P are relatively prime to each other, this can be written in this fashion. The first term does not change. The second term can be written like this, phi of P into phi of D. Here it is phi of P power E into phi of D. Then this is a common factor. If this is taken outside, we have 1 plus phi of P plus phi of P squared plus etc. all the way up to phi of P power E. But this is a sum that we have just seen. Since 1 is the same as phi of 1, it is identical to this sum, which we know evaluates to P power E. Therefore, this is the quantity within the square brackets, which is sigma D that divides k of phi of D into P power E. But this quantity inductively we assume is k. Then we have the sum reducing to k into P power E, which is nothing but n, and that is what we seek to prove. So, the case for P power E is the basis, and inductively here we apply the hypothesis that this sum evaluates to k, therefore, the induction holds. So, inductively we prove the statement. For example, let us say n equals 24, then the divisors are 1, 2, 3, 4, 6, 8, 12 and 24. Phi of 1 is 1, phi of 2 is 1, phi of 3 is 2, phi of 4 is 2, that is 1 and 3. Now, phi of 6 using the formula would be 6 multiplied by 1 minus 1 by p for every prime. So, 2 and 3 are the primes which go in 6. So, you have 1 minus 1 by 2 into 1 minus 1 by 3, which is 6 into half into 2 by 3, which is 2. So, phi of 6 is 2. Phi of 8 similarly is 4. Phi of 12 is 12 into half into 2 by 3, which is 4. Phi of 24 is 8. So, summing all these values 1, 1, 2, 2, 2, 4, 4 and 8, you find that the sum comes to 24. Taking a larger example, consider n equals 3000, then the factors would be 1, 3000, 2, 1500, 3, 1000, 4, 750, 5, 600, 6, 500, 8, 375, 10, 300, 12, 250, 15, 200. So, those are some of the factors. If you compute the corresponding phi values, you find these are 3000 you can see that the phi value is 800, 1500 it is 400, for 1000 again it is 400, for 750 it is 200, 600 is 160, 500 is 200, 375 is 200, 300 is 80, 250 is 100, 200 is 80. The remaining factors would be 20, 24, 25, 30, 40, 50. 50 into 60 is 3000, 40 into 75, 30 into 100, 25 into 120, 24 into 125, 20 into 150. So, the corresponding phi values would be 8, 8, 20, 8, 16, 20. For 150 it is 40, for 125 it is 100, for 120 it is 32, for 100 it is 40, for 75 it is 40 again, for 60 it is 16. So, these are the phi values. If you add up all the phi values together, you find that the sum comes to 3000 again, which is what n is. By Zm, we denote the integers modulo m, that is Zm is 0 through m minus 1. The cardinality of Zm would be m. So, as you can see, Zm is a complete residue system modulo m. We can define the addition operation on Zm thus. You can draw up a table. So, here let us consider the table of Z5. So, 0 plus x is x, 1 plus 4 is 5, which is 0 modulo 5, two plus 4 is 6, which is 1 modulo 5, 3 plus 4 is 7, which is 2 modulo 5, 4 plus 4 is 8, which is 3 modulo 5. So, this is the addition table for Z5. When we come to the multiplication operation on Z5, zero into x is 0. So, the top row is all 0. Similarly, the leftmost column is also all 0. 1 into x is x. So, here we have values in this fashion. Now, 2 into 2 is 4, 4 is 4 mod 5, 2 into 3 is 6. So, we have 1 mod 5 here, 2 into 4 is 8, which is 3 mod 5. 3 into 2 is 6, which is 1 mod 5, 3 into 3 is 9, which is 4 mod 5, 3 into 4 is 7, which is 2 mod 5, 4 into 2 is 8, which is 3 mod 5, 4 into 3 is 7, which is 2 mod 5, 4 into 4 is 16, which is 1 mod 5. So, this is the multiplication table on Z5. So, from the table, you find that 4 into 4 is 16, which is 1 mod 5. For example, that is 4 is a solution of 4x equals 1 mod 5. Recall we solved such equations using Euclid's algorithm. GCD of 5 4 is the same as GCD of 4 1, which is 1. Therefore, 1 is 1 into 5 minus 1 into 4. If you take mod 5 on both sides, you have 1 congruent to 4 into minus 1 mod 5. So, minus 1 is a solution for this equation. So, x congruent to minus 1 mod 5 is a solution. But then minus 1 is congruent to 4. So, this is the same as x congruent 4 mod 5. Let us now consider some quadratic congruences. X squared plus 2x plus 1 is congruent to 0 mod 4. The complete residue system mod 4 has 4 members. This is one complete residue system. So, we can try its members. So, when x equal to 0, we have 0 squared plus 2 into 0 plus 1, which is 1. This is not congruent to 0 mod 4. So, 0 is not a solution. So, if you put 1 here, we have 1 squared plus 2 into 1 plus 1, which is 1 plus 2 plus 1, which is 4, that is 0 mod 4, which means 1 is a solution. If you put 2 in, we have 2 squared, which is 4, plus 2 into 2, which is 4, plus 1. So, that is 8 plus 1, 9, which is 1 mod 4. So, this is not a solution. When you have 3 into 3, 9, 2 into 3, 6, plus 1, which is 16, which is 0 mod 4. So, this is a solution 2. So, 1 and 3 are 2 solutions for this quadratic congruence, and modulo 4, these are the only solutions. Modulo 4, there could be 4 solutions. We have tried all of them and we found that only 1 and 3 are solutions. Why? What we have seen earlier, if for in any complete residue system modulo 4, there will be exactly 2 members that are solutions for this quadratic congruence. Those 2 solutions would be congruent to 1 and 3 respectively modulo 4. Consider another quadratic congruence. Again, we are considering CRS modulo 4. So, we can consider the members of a CRS 0, 1, 2, 3 or members of Z4. Then when you plug in these values for x, from 0 you get 1, from 1 you get 1 plus 1, which is 3. From 2 you have 4 plus 2, 6 plus 1, 7, 7 mod 4 is 3. And then from 3 you find 9 plus 3, 12 plus 1, 13, which is 1 mod 4. So, we find that none of them will provide a solution. So, this quadratic congruence is without a solution. So, it is possible for congruences to have no solution. Consider another one, x squared plus 3x plus 1 is 0 mod 4. This is what we want to solve. Again, when you consider 0, 1, 2, 3, you find that the values are 1, 1, 3, 3. Again, there is no solution. If you consider 2x squared plus x plus 1 equals congruent to 0 mod 4, if this is the case, then for 0, 1, 2, 3, you find that the values are 1, 0, 3 and 2. So, there is a unique solution here. 1 is a unique solution. Consider x squared minus 1 congruent to 0 mod 8. So, here the members of Z8 would be 0, 1, 2, 3, 4, 5, 6 and 7. So, if you evaluate here for 0, x squared minus 1 is minus 1, which is 7 mod 8. For 1 it is 1 minus 1 0, for 2 it is 4 minus 1 3, for 3 it is 9 minus 1 8, which is 0, for 4 it is 16 minus 1 15, which is 7 again, for 5 25 minus 1 24, for 6 35, which is 3, for 7 it is 49 minus 1 48, which is 0 mod 8. So, you find that there are 4 solutions. So, the solution set is 1 3 5 7. So, you find that the number of solutions could be larger than the degree of the polynomial. So, here we have a quadratic polynomial, but the number of solutions is 4. Regarding polynomial addition and multiplication, consider these two polynomials over Z5. Let us say f of x is 6x cube minus 4x squared plus 5x minus 4. G of x is 3x cubed plus x squared minus 6x plus 1. These can be simplified in this fashion. F of x is the sum of the first term is 6x cube, but since 5x cube for any integer x is divisible by 5, this can be written as x cube. Minus 4 is congruent to 1 modulo 5, so this can be written as x squared. 5x is divisible by 5, so we have 0x, and then minus 4 is congruent to plus 1 again, so we have plus 1. So, f of x can be written in this simplified form modulo 5. So, we say f of x is congruent to this polynomial modulo 5. Similarly, g of x is congruent to 3x cubed plus x squared. Minus 6x is the same as minus x, which is the same as plus 4x and plus 1. If you were to add these polynomials, the sum would be 4x cubed plus 2x squared plus 4x plus 2 mod 5. Once again, if f of x is 6x cubed minus 4x squared plus 5x minus 4 and h of x is 2x plus 7, then as before we can simplify them. F of x is congruent to x cubed plus x squared plus 1. H of x is congruent to, this is of course mod 5. F of x is congruent to 2x plus 2 mod 5 again. Then if you take the product f of x into h of x, you get 2x power 4 plus 2x cube plus 2x cubed plus 2x squared plus 2, which is 2x power 4 plus 4x cubed plus 4x squared plus 2. So, that is how you add and multiply polynomials in modular arithmetic. Now, let us study the ceiling and floor functions. The floor of x is defined as the greatest integer less than or equal to x, and the ceiling of x is defined as the smallest integer greater than or equal to x. For example, floor of 7.1 is 7, ceiling of 7.1 is 8. So, let us see a few results regarding the ceiling and floor functions. The first theorem says that floor of x is less than or equal to x, which is less than floor of x plus 1, and x minus 1 is less than floor of x, and 0 is less than or equal to x minus floor of x, which is less than 1. So, to prove this, suppose x is n plus epsilon for an integer n and an epsilon which is between 0 and 1. Epsilon could be 0, but epsilon is less than 1. Then the floor of x is the floor of n plus epsilon, which is n. This is less than or equal to n plus epsilon naturally, because epsilon is between 0 and 1, but this is what x is. So, we have that floor of x is less than or equal to x, but x is n plus epsilon, which is less than n plus 1, because epsilon is less than 1. This is, as we have seen, n is floor of x, so this is floor of x plus 1. So, which proves the first line here. X minus 1 is n plus epsilon minus 1, which is less than n, which is less than or equal to n plus epsilon, which proves the second line. 0 is less than or equal to n plus epsilon minus n, because epsilon is greater than or equal to 0. This is of course epsilon, which is less than 1, which proves the third line. Floor of x is also equal to the sum over 1 less than or equal to I less than or equal to x, where I is an integer of 1. So, as the proof, consider x is n plus epsilon, where epsilon is as before, then floor of x is n, that is what the left hand side is, then sigma 1 less than or equal to I less than or equal to x for integer I would be n. Thirdly, the floor of x plus j is the floor of x plus j for any integer j belonging to z, any j belonging to z. Say x is n plus epsilon, where epsilon is as before, then 4 of x plus j would be the floor of n plus j plus epsilon. N is an integer, j is also an integer, so n plus j is an integer. So, this would be n plus j. Floor of x is n, so the right hand side is n plus j, which is the same as the left hand side. The next theorem says that floor of x plus floor of y is less than or equal to floor of x plus y, which is less than or equal to floor of x plus floor of y plus 1. Let us say x is n plus epsilon and y is m plus delta, where 0 less than or equal to epsilon and delta, which are less than 1. Then n plus m, this is what floor of x plus floor of y is. This is less than or equal to floor of x plus y, which is n plus m plus epsilon plus delta. So, depending on epsilon and delta, this is either n plus m or n plus m plus 1. So, indeed the first inequality holds, n plus m is less than or equal to this, and this is less than or equal to n plus m plus 1, which is what floor of x plus floor of y plus 1 is. Therefore, the second inequality too. Floor of x plus the floor of minus x equal to 0 if x is an integer, is minus 1 otherwise. So, let us consider a non-integer first. Suppose x is n plus epsilon, where epsilon is neither 0 nor 1, it is strictly between 0 and 1, in which case floor of x is n, floor of minus x is floor of minus n minus epsilon. So, we are looking at the integer which is smaller than this, but is the greatest, that will be minus of n plus 1. Therefore, when you take the sum, you have n plus minus of n plus 1, which is minus 1. Now, if x is an integer, floor of x is the same as n, minus of x is minus n, the floor of minus n is minus n, therefore, the sum would be 0, as the theorem claims. The floor of x by j is floor of x by j if j is a positive integer. To prove this, let us assume that x is n plus delta for an integer n and 0 less than or equal to delta less than 1. Suppose n is qj plus r. For any n and any j, we can write n as qj plus r, where r is greater than or equal to 0, but less than j. Then x is qj plus r plus delta. Now, let us consider the left hand side. The ceiling, the floor of x is qj plus r. So, we have the floor of qj plus r by j, which is the floor of q plus r by j. Since r is less than j, this fraction r by j is strictly less than 1, therefore, this would be q. So, the left hand side is q. Now, the right hand side is floor of x by j, which is floor of qj plus r plus delta divided by j, which is q plus r plus delta by j floor. But r plus delta is less than j. R is less than j, so r can be at most j minus 1, and delta is strictly less than 1. So, r plus delta is less than j. Therefore, the fraction r plus delta by j is less than 1, so this would be q, which is the same as the left hand side. So, the theorem is then proved. The seventh result would be this: the negative of the floor of minus x is the same as ceiling of x. Say x is n plus epsilon for 0 less than epsilon less than or equal to 1. Note, here I have taken epsilon as strictly greater than 0, where n is an integer. Then ceiling of x is n plus 1. This is what the right hand side is. Minus of x is minus n minus epsilon. The floor of minus x therefore is minus n minus 1. The negative of that This is what the left hand side is. That will be n plus 1, which is the right hand side. Hence, the result holds. The floor of x plus half is a round of x where halves are rounded upwards. For example, round of 7.5 is 8 because a half is rounded upwards. To prove this, first consider x equal to n, there is no fractional part. Then floor of x plus half is the floor of n plus half, which is n. But this is the same as round of n. Since x is an integer, round of x is the same as round of n. If x is n plus epsilon, where epsilon is greater than 0 but less than half, then floor of x plus half is the floor of n plus epsilon plus half, which is n. Epsilon is less than half, so epsilon plus half together will not make up 1, so the floor here is 1. Floor here is n, which is the same as round of x. Since epsilon is not large enough, the round function will not round upwards. If x is n plus epsilon, for epsilon that is greater than or equal to half but less than 1, floor of x plus half would be floor of n plus epsilon plus half, which is n plus 1, which is the same as round of x. So in this case epsilon could be half, in which case x would be rounded upwards. Analogously, negative of the floor of negative x plus half is round of x, where halves are rounded downwards. The proof is a dual of the previous one, so I leave it as an exercise. Another result about ceiling and floor is this: for n and m belonging to z plus, the set of positive integers, floor of n by m is the number of integers in the range 1 to n divisible by m. Say n is qm plus r. For any two positive integers n and m, we can write n as qm plus r for r that is greater than or equal to 0 but less than m. Then floor of n by m is the floor of q plus r by m, which is q because r by m is less than 1. So integers in 1 to n divisible by m are they will form the set m, 2m, 3m, etc. up to qm. N is qm plus r, therefore n is greater than or equal to qm. So there are q of them, hence the theorem. For n m which are in z plus, floor of n by m is the same as the ceiling of n minus m plus 1 divided by m. So again assume that n can be expressed as qm plus r as before. So floor of n by m is the floor of Qm plus R by M, which is floor of Q plus R by M, which is Q, as we have seen before. Then the ceiling of n minus m plus 1 by M would be the ceiling of Qm plus R minus M plus 1 divided by M, which is the ceiling of Q minus 1 plus R plus 1 by M. This is Q minus 1 plus a fraction epsilon. R plus 1 by M is less than 1 when R plus 1 is less than M, and therefore this quantity will be Q. This would be ceiling of Q minus 1 plus 1, which is the ceiling of Q, which is again Q, if R plus 1 equal to M. Since R ranges from 0 to R minus 1 both inclusive, R plus 1 is either less than 1 or is equal to M, either less than M or is equal to M. So these are the only two possibilities. In both the cases we find that the right hand side evaluates to Q, hence the theorem. So that is it from this lecture. This is the last lecture of the module in number theory. Hope to see you in the other modules. Thank you.